Okay, so what we're going to be talking about today is just the early models of the atom. So before we actually get into the models of the atom, so I have cohort A. You're going to be talking about the parts of the atom first with me on Monday, Tuesday, and then you'll be going into the early models of the atom. So you guys will see this after. Cohort B, you guys are going to go ahead and start this Monday and Tuesday. And what we're going to be discussing is how we got to the atom we have today. Okay. And so the objectives that we have is we're going to discuss early developments of the atomic theory. So Democritus, Dalton, Thomson, Millikan, Chadwick, Goldstein, Rutherford. Okay. We're going to be drawing and labeling models of the atom. All right. And so you're going to be able to describe problems associated with each one. And then we're going to describe the equipment used and the experiments done by Rutherford, Thomson, when it talks about early models of the atom. So originally we had a guy named Aristotle. So if you think about way before, so when people were thinking about materials, they didn't have the science we did today. So what they were thinking of is, well, okay, so how did things work? What was things made up of? And so fundamentally, we used ideas. Okay, so we had a Greek philosopher, Aristotle, who said all matter is made up of earth, wind, fire, and water. Okay, it was a very basic understanding, but it made it easy for people to get behind. But before Aristotle's, we actually had a guy named Democritus, who was before his time. Okay, and what Democritus was is he was also a philosopher. Okay, but he believed that all matter was made up of tiny, indivisible, indestructible particles. And so if you think about it, what he was saying was if I took a sheet of paper and I ripped it, and then I took half of it away, and then I ripped the one half into a quarter, and then I took the quarter and ripped it into an eighth, and then a 16th, okay, and I kept going, at what point can I never rip it anymore? And so Democritus was thinking, well, okay, at some point it stops. And so he made this term called the atoms or the atomos. Okay, so he gave atoms the properties that resulted in shape, size, and motion. So that's crucial. If I were you, I would star or underline that. And he called these particles atoms. Okay, and so what he said is, well, like oil must have been smaller circles compared to water because it's more slippery. And like solids must have been like ninja stars, and they were all just clumped together because you can't break apart many solids. So he was thinking the atoms must have been interlocking somehow. The only problem with Democritus is he had no experimental evidence, okay, and they couldn't explain chemical behavior. So if I took like baking soda and vinegar, you guys have done that before. If I mix them together, they couldn't explain why it made bubbles. So there was a couple things wrong with Democritus. Now, if you think about it, Aristotle came after, all right? And so he actually came after Democritus, and because he was a student of Plato's, they actually believed Aristotle's model compared to Democritus. So it just kind of shows science sometimes takes a back step, and this was one of those moments. But Democritus was ahead of his time, even before Aristotle's. And then we get to John Dalton. And John Dalton revolutionized science because he used experimental evidence. Okay, he based his work on law of conservation of mass, and what that states is whatever I start with is what I end with. I can't start with 10 grams of water and then somehow end up with 8 grams of water and 2 of it just disappear. Doesn't make sense. So John Dalton revolutionized it because his experimental evidence. Okay, and so he said atoms were indivisible and homogeneous. Okay, they were the same throughout. So atoms of an element are identical to each other and different from other elements. So basically he was saying all hydrogen atoms were the same, all oxygen atoms were the same, but oxygen compared to hydrogen, they were different. Okay. And then he came up with compounds formed whole number ratios. So he would have said water was H2O. He would have been the first one to come up with the formula of water. Okay, not saying he did, but that's what he was coming up with is those whole number ratios. Now, he also said reactions rearrange atoms, okay, but they do not change the type of atoms. So he was saying in a chemical reaction that hydrogen and oxygen could be split and put into other element or with other compounds, but hydrogen couldn't change to helium physically. It wasn't possible. Okay, so he believed in the rearranging of the atoms. Okay. Now, what his model was, and this is John Dalton's model, so you need to write this up at the top. His was the billiard ball model or the ball and hook model. Okay, and so he believed that these atoms would have these little hooks that would allow them to connect. All right, we didn't understand why atoms of different elements could physically combine to make compounds. We didn't know that. So his problems were atoms were divisible. All right, we know that, and we will learn that when we get to nuclear decay. And then he still could not explain chemical behavior. So he couldn't explain why certain things were reacting and some weren't. Okay, so he still had the same problem with Democritus. So if we go, we have J.J. Thomson was next. Okay, J.J. Thomson used experimental evidence. Okay, he used what's called a cathode ray tube. So you can see it right here is our cathode ray tube. He filled it with a gas, okay, and it was a green gas, fluorine. And then what he did is he shot an electric current through it. And so the current should have gone straight, okay? But how he detected if it had any electrical proponents to it, he took a magnet, and obviously if you know magnets, like charges attract, so a positive will attract a negative, and like charges will deflect. So a negative will repel a negative, and a positive will repel a positive. Well, knowing what we know about magnets, he stuck it up to the electric current, and what he saw is the gas actually was attracted. And so if he used a negative magnet, he determined that it was a positive particle, but what he used was a positive magnet, and he actually saw that there was a negative component because the positive drew in, and we know it can only attract the opposite charge. And so we see this light gets attracted to it, and it goes towards the magnet. So knowing what that side of the magnet was, being a positive, we found out that there was negative components to atoms. Okay, and so moving on. So he determined that beams are made of particles coming from the atoms in the gas, which we know that everything is made up of atoms. And then the particles must be negatively charged because he saw using a positive magnet that it attracted those atoms. Okay, and so the beam went closer to that magnet. And so what he called it was corpuscles, and we now call them electrons. Okay, now only problems is what remained after the electron. So your biggest thing is J.J. Thomson found the electrons in an atom, but what remained to the electrons? Well, if they were all electrons, by theory, all negative particles should repel. So we knew that there had to be something positive in there. Something had to be attracting those negatives together. So, and we could not explain the chemical behavior. So his model was what we call the plum pudding model. So he showed that all these negatively charged particles, okay, were in the atom. And the only thing that was keeping them together, he said, well, maybe it was in a sphere that was all positive. That would make sense, right? So that was J.J. Thomson's theory, and his model is the plum pudding model. So you need to know three things. What he found, electron in the atom. Okay, what his model is, it's the plum pudding model right here. And what equipment was used, and it was the cathode ray tube. Those are the three things you need to know about J.J. Thomson. Okay, Robert Mulliken, you're probably not going to get tested on this, but it is something you need to know. Okay, Robert Mulliken found experimental evidence of a charge and the mass of an electron. Okay, and so he used what's called an oil drop experiment. So they ionized a certain atom, and essentially they put two like plates, and they used ionization. Essentially, they levitated electrons, being able to calculate its electrons mass. So that's all you need to know. Robert Mulliken found the electron charge and mass. Then we have Eugene Goldstein. Doesn't get a lot of credit, but he actually found the protons. And so he used the same thing that J.J. Thomson used, but he did a different cathode ray tube. And what he found is there was rays traveling the opposite to the cathode ray. So basically, J.J. Thomson found those negative particles. He found that there were particles moving the other way. And so what they concluded is they had to be positive particles. And so you just need to know Eugene Goldstein found the proton. And you need to write that down. He is found experimental evidence of the proton. That's all you need to know with Eugene Goldstein. Then we have Ernest Rutherford. This guy is a genius, okay? And so all you need to know is he had what's called the gold foil experiment. And so he used uranium. Reason being is it gives off a helium alpha particle. And so what he did is he put this uranium in a lead box, and they put a little hole in one side of the lead box. And if you know anything about lead, it is very dense, so no particles or rarely any particles can get through. And so they put a hole, so the only place for helium particles to go out was through the one hole. And so they directed it towards a gold foil. And what they did is they put all of this, they put like a detector, an atom detector, to see what would happen. Now, what they theorized based on J.J. Thomson's theory of the plum pudding model, he theorized that if his model's true, all of these atoms should have gone through. Okay, reason being is because they were shooting a positive particle through a negative atom. So it should have just gone right through. And so there should have been no deflections. Well, what they actually saw is they were deflecting parts of the atoms. Now, well, think about it. You shoot a positive particle. Well, knowing anything about magnets, the only thing that could deflect was something that was solid. So if I throw a ball at a wall, okay, it's gonna come back. So for something to deflect, one had to hit something, and two, it had to be the same charge, because we know like charges repel as well. So the gold foil experiment, what he found was a dense small nucleus. So if we look, and I'm going to zoom in, these alpha particles had to hit something solid. So all of these gold circles are this gold circle here. So they're their own atoms. So they all have a nucleus. And so each nucleus was deflecting some of these helium particles. So if we go to what Ernest Rutherford is known for, the experiment is the gold foil experiment. And what he resulted was a nuclear model of the atom. He found experimental evidence of a small, dense, positive nucleus, and he said that they were surrounded by electrons. So he said atoms are mostly empty space. So if you think about it, an example that I like to use is think of the solar system. Okay, the sun would be the nucleus of the atom, and all the planets would be revolving electrons. And that's how he saw the nuclear model of the atom, using his experimental evidence. Okay, and so you can see this would be the sun technically, and then all of these would be electrons or the planets revolving around the sun. Okay, so to put it into perspective, why he said atoms are mostly space, if we look, 99% of the particles went through the gold foil. In almost less than 1% got deflected. So if most of it's going through, he had to determine that the atom had to be mostly empty space. So the relative size of the nucleus in the atom, well, if you think about any stadium, so if we said the Horseshoe, the Ohio State Stadium downtown, if you put one marble on the 50-yard line, that is how small the nucleus is compared to the rest of the atom, to put it into perspective. So a little bit mind-blowing if you think about it. Now, his model of the atom, so this is Ernest Rutherford's model of the atom. So three things you need to know is can't even speak. His experiment is the nuclear model or the gold foil model, okay, or the gold foil experiment. His model is the nuclear model of the atom, okay, and what he found was a dense positive nucleus. Okay, so he came up with the nuclear model of the atom. This is Ernest Rutherford. His problem is he still could not explain chemical behavior. Now look at the time that Ernest Rutherford came up with this model. So not even 100 years ago, we couldn't explain chemical properties. We couldn't explain why baking soda reacted with vinegar. It made gas, but we couldn't explain why. Okay. And then the last one that we go ahead and talk about is James Chadwick. And so in 1932, he just found experimental evidence of the neutron, and it came last because it has no charge, so it wouldn't react to any magnetic properties. And one, you can't see it. So just know that James Chadwick found the neutrons in the atom. Okay. So what I want you guys doing is go ahead and do your vocabulary. It's posted under week 7 in Google Classroom. It is due by the end of this week, so it's due Friday, and that's for both cohorts. So make sure you go ahead and submit the vocab by Friday.